After understanding the structural reliability theory from the previous lectures, we are now continuing with lecture 14 on module 2. Where we will take up an application problem. This problem and solution will be discussed in 2 lectures. I call them as application problem number 1, and of course, the next lecture will be application problem continued on the same problem. Okay. So, welcome back to the 14th lecture on module 2 on the online course Risk and Reliability of Offshore Structures. As I said, in general, offshore structures have uniqueness because they are form dominant design. Recent developments in offshore platforms have shown very high dependency on different kinds of structural forms. I can quote some examples, starting from new generation platforms like tension leg platform, where buoyancy exceeds the weight by a large amount, triceratops, where the hull or the top side hull and the buoyant legs are isolated using hinged connections, or let us say ball joints, etc. So, there are classical examples in the literature which shows that the recent development of offshore platforms are more form dominant than they are function dominant as used to be earlier. Okay. So, now let us take up one example of application of reliability problem. We will consider a tension platform for our discussions now. We already know tension platform is a compliant system, is a compliant offshore platform, which is also called as an hybrid platform. Because of one essential reason. I will tell that reason very quickly, which you remember from the first module lecture, but still. Okay. So, let us say I have a platform consists of pontoons and column members. Let us say these are all column members. Okay. Let us say, let us assume a rectangular platform in shape. So, I have 4 column members as I showed here, and I have pontoon members on the bottom as well as on the top, and the top side will now consist of all details as required, maybe a crane derrick, okay, maybe a helipad, and so on. Okay. It is a multi-tier system, let us say the machine room, etc., all complications. So, the water level approximately is here, that is the mean sea level. So, now the system has a mass, let us say, which is acting downward, therefore, the weight, which will be now balanced by, of course, the buoyancy force. Now, we already said in the design, buoyancy force exceeds the weight of the platform by a large amount. That is an advantage of this. When the buoyancy force, we all know that buoyancy force actually is a function of submerged volume, or you can say displaced volume. Okay. So, displaced volume depends upon the surface area of the circular member and the depth of immersion, what we call as a draft or design draft. So, the volume of the system, the submerged volume depends upon the size is very large and the diameter is again very large. So, it has got a very large displaced volume, therefore, buoyancy is of very excess compared to the weight. The advantage is when buoyancy exceeds the weight, the platform can set afloat very easily, therefore, transporting, erecting, commissioning becomes easy. Okay. However, when you want to install the platform in position for oil exploration, then the station keeping is very important. So, we hold down this platform using teethers. Which will be supported at the bottom and anchored to the seabed firmly. So, when the platform is brought in position, these teethers will be all slackened, okay, all will be loose, there is no initial tension in them. So, there is a design draft which I can mark here, this is my design draft, let us say dr. Okay. I add more weight to the top side, so the platform will start immersing further. So, the cables, all the teethers, these are all teethers, will be all slackened, they will be loose. So, the teethers will be connected to these points firmly. Once the excess weight is removed, the platform will be pushed up by the buoyancy force, and these teethers will not allow the platform to move up. Okay, they will pull down the platform, that is why they are called tension legs. So, the initial tension given in the legs is what we call as T0. So, T0 is the initial, I should say, pretension in teethers, east teethers, let us say. Okay. So, now if you write the equation of static equilibrium for this particular platform, I should say W and Fb are not matching, because W is far lesser than Fb, but I want to match this, I want to equate this. So, I add T0 and say this is my Fb. So, since there are 4 legs, I should multiply this with 4 T0. Okay. So, W is acting downward, T0 is acting downward, Fb is acting outward. This is my equation of static equilibrium. So, interestingly, I am looking at the safety of the platform, okay, during its functional intended use. As I said, reliability is assessing or guaranteeing or ensuring performance of a system in terms of its functional operation when it is demanded to perform at a specific time under specific conditions. The specific conditions in our discussion is nothing but the sea state where it is being commissioned. So, we would like to check whether the safety of the platform is ensured during operation. To ensure this, I must check whether the platform remains safe and well conditioned under the installed commissioning stage. Okay. Now, therefore, station keeping characteristics the station keeping characteristics essentially come from the measurement of T knots or teethers or compliance of teethers for the given loading imbalance. So, station keeping characteristics of the platform need to be examined. Okay. We try to examine this under extreme load combination. Because under extreme load combination, this can cause imbalance to the teethers or tension in teethers, which in turn will affect the stability of the platform, because that is the equation of static equilibrium of the given platform. Okay. Therefore, reliability sometimes also checks the safety of the platform under intended operation. So, this is maybe the reliability index may not be computed from this problem, but safety of the problem under extreme load combination will be verified, which is also of course essentially part of the reliability study. Okay. To do this, we can assess the stability of the platform using Matthews stability one can study this using Matthew stability. So, the example what we will now discuss will assess a tensionless platform of a given installed platform in the C state of a known C state. We will assess the stability of the platform in terms of its functional safety. Okay. So, therefore, this is going to be a dynamic analysis of tethers and TLP as a system, considering a linearly varying tension along the tether length. Okay. So, now we are going to check the stability using dynamic analysis of the system is carried out by considering. So, to challenge the dynamic stability of the system, there should be a variable, is it not? That variable is going to be by considering linearly varying tether tension. Along its length. So, that is the variable here. Okay. T0 is the variable. To ensure this, we perform modal analysis. We need to perform modal analysis. Okay. Considering the linear cable equation for the tether model. Which may be a simplified approach, does not matter, but let us look into this as an example study. Okay. So, we will pick up 3 tensional platforms installed at various water depths, because we would like to know the parameters on which this variable is dependent. Okay. Then only we will be able to establish the cross correlation effects of each of this variable under the action of these parameters. So, we will consider 3 TLPs installed at different water depths. Okay. For example, the water depths are 527.8 meters, which are real TLPs. I will give you the examples later. 872 meters and 1200 meters. Okay. What we are looking at is, the objective is to obtain the amplitude of theta vibrations. Theta vibrations. Okay. And also to examine the unstable modes of vibration. Okay. So, we perform Matthew stability analysis. For TLPs, I should say. Okay. The resultant modal form of tether dynamic model will be then obtained in the form of Bessel function. Okay. So, the resultant modal form of tether dynamics will be obtained in the form of Bessel's function, because then it is easy to check the stability. As we all know, in engineering practice, wherever we start any problem, numerical, analytical, experimental, we always have set of assumptions or idealization. So, the following assumptions are made. Okay, let us see. Static tension vary linearly along the length. Length of the theta due to the effect of own submerged weight. Okay. We are looking at the tension variation due to two cases. One is because of the submerged weight on its own, one is because of the variation in response of the system itself, because it is a compliant system. Okay. 2, the end conditions are considered as simply supported. Okay. Of course, we consider only the hydrodynamic load, current effects are neglected. Only the wave load is considered. We also neglect the flexural rigidity of the theta. Because it is very slender. Once the flexural rigidity of the theta is neglected, its lateral moment is then given by a specific equation. Let us do this. So, under the following assumptions, let us say while assumption 4 is valid, that is flexural rigidity is neglected, the lateral moment of the theta under lateral loads, okay, is given by the following governing equation. I can say m dou square y by dou t square minus dou by dou x of Tx dou y by dou x plus Bv dou y by dou x mod dou y by dou. Okay. Now, let us see equation number 1. In this case, m is the theta mass per unit length of the theta. This includes physical plus added mass, if any. Added mass will come due to the submergence effect. Bv is the fluid damping coefficient which is quadratic. Tx is the total tension. Now, the total tension acting along the theta is composed of two things. One, it will be due to the static tension, which I call as T0 x. T0 stands for initial pretension or static tension, which results from the pretension imposed on the platform. Okay. The second could be the varying tension along the tether length. Which we call dynamic tether tension variation. Okay. So, the varying tension along the length of the tether due to the action of the submerged weight. Okay. Now, one can now say T0 x is P plus mu g L minus x, where P, let us see equation 2, is platform pretension, mu is the physical mass per unit length, L is the tether length. The dynamic tension, the second component, is given by T dx, which is minus S cos omega t, which is imposed by the first order heave motion caused by waves with frequency omega. In this case, S is wave induced tension amplitude, therefore, total tension which I need to substitute in equation 1, that is T x is P, that is T 0 x plus T d x, which is P plus mu g L minus x plus minus S cos omega t. Okay. Now, the equation for tether's free lateral vibration is given by m dou square y by dou t square minus dou t x by dou x set to 0, which is equation number 5. Now, assuming the lateral motion of the nth natural mode as yn of x of t can be written as fn of t xn of t. Now, let us substitute 6 in 5 above. Rather, let us modify substituting equation 6. The equation of motion what initially we proposed in equation 1 will be now modified as p by m plus mu g L minus x by m of xn plus omega square xn is 0. Let us say equation number 7, where omega bar n is the natural frequency of the nth mode. Now, this dynamic model shown in equation 7 leads actually to a classical Sturm-Liouville problem. So, to solve this, let us introduce a new variable eta, where eta is 1 plus mu g L minus x by p. Equation 8. Now, substituting equation 7 can be rewritten as eta square xn plus eta n xn plus 4 beta n eta square xn is 0, where beta n can be said as Pm by mu g square omega n square. Equation let us say 9a. If you look at the equation 9 closely, equation 9 is actually a modified form of Bessel equation. the solution of a Bessel equation can be given in form of Bessel function. Okay, which in this case is J0 Y0. So, x and n is C1 J0 twice beta n is going to be eta plus C2 Y0 twice eta. So, equation number 10, where C1 and C2 are constants which can be determined from the boundary conditions. So, what are the boundary conditions? X and eta r equals 0 is 0 and x n eta r equals 1 is also 0. Both ends are simply supported. Okay. Therefore, the resulting model for a tether dynamic equation as given by J naught twice beta n 1 plus mu g L minus x by p to the power half minus J0 twice beta n by Y0 of beta n of Y0 of, okay, I will write the term here, minus J0 twice beta n by Y0 of beta n of Y0 twice beta n mu g L minus x by p half. Equation number 11. The frequency omega bar n will be given by mu g 1 by p m of beta n. Equation number 12. Now, the value of beta n can be determined numerically. Because the solution numerically. The solution of the characteristic equation is given by. That is the reason why we can get beta n numerically. J 0 twice beta n 1 plus mu g L by P y 0 twice beta n minus y 0 twice beta n top 1 plus mu g L by P j 0 twice beta n set to 0, equation 13. Substituting the value of the above equation in the original equation of motion what we had. Now, by substituting these values, equation 1 will be modified using Galerkin's variation method. So, it is nothing but multiplying it with x n x, x n of x, and then integrating it along the tether length. So, now we need coefficients to do this. Let the following coefficients be determined. I1, which is along the length we have to integrate, along the length 0 to L. So, x n square dx. Okay. Let us say I2 is again 0 to L dxn by dx of xn dx. Let us say I3 0 to L d square xn by dx square xn dx. Let I4 be 0 to L d square xn by dxn square of xn x dx, and let us say I5 is 0 to L x cube x dx. Okay. Equation 14. Now, with these coefficients in place, equation 1 it is modified to a new form. So, which is plus del minus q cos 2 tau of f plus c df by d tau 0. Let us say I will call this equation number 15, which is a modified form of equation 1. In this case, in the above equation where tau is a dimensionless time variable, which is 2 tau is omega t. Now, the tether dynamics will be now expressed represented by a Matthews parametric equation where there are two parameters. Let us say what are these parameters? Delta n, which is given by 4 by m omega square of mu g I 2 plus I 4 by I 1 minus P plus mu g L I 3 by I 1 q n, which is equal to minus 2s by m omega square I 3 by I 1, which is further equal to B v by m I 5 by I 1, equation number 16. Now, the dynamic analysis will be performed assuming an induced dynamic tension amplitude in the given problem, which is as per the real case analysis what you are going to do to assess the safety of the system, stability of the given system under the normal loading operations and operating conditions. The dynamic analysis will be now performed under induced tension vibration, induced dynamic tether tension, right. As an extreme case, because we are looking for a failure case, it is an extreme case, the dynamic tension amplitude equal to 60% of the nominal static tension will be imposed. Why it is done? As an extreme case. To induce failure, is it not? So, we are going to check it. So, therefore, it is a safety study. So, we will apply this to a set of TLP examples and we will plot the Matthews stability curve and show whether the induced tension as an extreme case results in failure or safety domain of the TLP, which we will discuss as a continued problem in the next lecture. Thank you very much.